Inside a modern computer, RAM acts as a massive warehouse. It holds gigabytes of data, but retrieving information requires a physical trip across the motherboard. Compared to the speed of a processor, that trip is agonizingly slow. If a CPU had to wait for RAM every time it performed a calculation, its processing power would drop to a fraction of its advertised potential. The system would spend most of its life waiting for data to arrive. To solve this, engineers built a tiny, ultra-fast workspace directly on the processor chip. It is called the register file. Systems like ARM rely on a strict workspace. While RAM holds billions of bytes, this on-chip file typically consists of exactly 32 registers to hold the data currently in use. Keeping math local is the only way a CPU can maintain its lightning-fast clock speeds. The bottleneck is no longer the distance to external memory, but how effectively the processor manages this tiny internal space. Processors overlap work, simultaneously fetching, decoding, and executing commands. Superscalar processors take this further, executing dozens of pipelines at once. This creates a physical conflict. Every parallel pipeline must access the exact same 32-slot register file simultaneously. The risk is total data loss. If two instructions interact with the same register simultaneously, without perfect control, the data is overwritten and permanently destroyed. The demand for speed has turned the register file into a volatile traffic intersection. Without precise management, the very mechanism meant to accelerate the system would cause it to crash. Managing that intense data traffic requires complex, microscopic routing networks that are physically built directly into the silicon of the processor itself. At its core, the register file is an array of memory switches called D flip-flops. Multiplexers select and extract data from these registers, while decoders coordinate precise write commands, timed perfectly to the system clock. A standard setup usually includes 2 read ports and 1 write port. For simple processors, this 3-port architecture is efficient and stable. But to increase speed, engineers must add more read and write ports to allow more instructions to access the file at the same time. This adds a physical cost, called the wire pitch area. While the space needed for transistors grows linearly, the space required for the overlapping wires increases squarely for every port added. Eventually, the register file becomes so large that the electrical signals have to travel further, which increases latency. Adding ports intended to increase speed eventually forces the CPU clock to slow down. Because engineers cannot bypass the physical laws of wire density, they use logical routing to circumvent them. One solution is register renaming. Hardware decouples the small list of code registers from a much larger pool of hidden physical registers. The processor dynamically maps data to empty physical slots, avoiding collisions without requiring a dense, power-hungry wiring layout. Another method is banked organization. Engineers split one large, slow register file into smaller, faster banks that use fewer ports. This requires scheduling algorithms that predict where data is needed. Organizing instructions in advance prevents different pipelines from fighting for the same bank. Performance depends on this internal traffic coordination. The register file is the physical boundary where electrical complexity must be reconciled with the demand for speed.